Welcome back, students. We are working on the mean value theorem for today, and from that we'll get the average value of a function. And the mean value theorem states that if f is a continuous function on a closed interval from a to b, then there exists a number c, and I annotated for you that that is an x value, that's in your closed interval from a to b, such that if you do the integral from a to b of f of x dx, it will equal f of c times b minus a. So as far as the mean value theorem goes, the f of c is the mean value. So I've tried to illustrate what is happening. If you draw a rectangle through the mean value, through the ordered pair c f of c, then the multiplication of the height of that rectangle, which is given by f of c, times the width of that rectangle, b minus a, would actually give you the exact area under the curve. And that is given by the integral. So I tried to show you a little bit better illustration here in the middle of your page. If we would draw a left endpoint rectangle, you'll see that this rectangle will underestimate this area right in here. And on the far right, if we draw a right endpoint rectangle, we have an overestimate, as you see happening in this little area. But a rectangle drawn through the mean value of the function, or through the average value of the function, has the same amount of overestimation as it does underestimation, and therefore provides an exact measure of the area under the curve. So if we can find that mean value of the function, then we have found that point through which we could find the actual area under the curve. So I'm going to go through a couple of examples that illustrate how to find the mean value of the function. And I have some steps for you to use both to find c, which is the x value where the mean value occurs, and f of c, which is the mean value of the function. That will be a y value. So it really just amounts to setting up an equation. And so step one is really the key to it. You'll be setting up an equation, and then your variable will be the f of c. That's what you'll be solving for. So we'll move to the back and work on your two examples. Your first example is f of x equals 9 over x to the third, and you're given an a of 1 and a b of 3. You'll want to do a rewrite of the function. The first thing you're going to do is set this up using the mean value theorem. So the mean value theorem says that you'll integrate from a to b, so from 1 to 3. I'm going to set this up so that I have 9x to the negative 3 and dx equals, and then I do not know f of c. That will be my variable, and then the b minus a is 3 minus 1. So now I can integrate, and doing the integration, I'll use the power rule. So I'll have 9x to the negative 2 power over negative 2, and this will be evaluated from 1 to 3. On the other side of the equal sign, I'm going to keep my equation. 3 minus 1 gives me 2 times my variable f of c. And I'm going to clean up the integral just a little bit, having negative 9/2 and putting that x with a positive exponent in the denominator, still evaluating from 1 to 3. So my next step will be to apply the fundamental theorem of calculus. So that is f of b. So I'm going to plug in, I'll have negative 9 over 2 times my b, which was 3 squared, and then minus f of a, so negative 9 over 2 times the 1 squared. And I still want to keep my equation, so equals 2 f of c. Continuing to evaluate, I have negative 9 over, that's 18, so that'll be negative 1/2. And then minus negative will turn to positive, and I'll have 9/2. Keeping my equation, that equals 2 f of c. And hopefully you can see the solution emerging from this. So negative 1/2 plus 9/2 is 8/2. That's going to be 4. So 4 equals 2 f of c. And I can divide both sides by 2, leaving me with 2 as my f of c. And so this is the mean value. The mean value of the function, and again, the mean value is a y. So the mean value of the function is 2. And now we're going to find where this mean value occurs. Now, it needs to occur between a and b, not necessarily at the midpoint. So don't assume, because it's a mean value, that this will occur at the midpoint of 1 and 3. To find the c value, which is what we're going to do next, we will set f of c equal to the mean value. Now, that just means that you're going to use f of x. So your original f of x, which was 9 over x to the third. But instead of x, I'm going to use c. So 9 over c to the third equals, and then my mean value, which is 2. So again, we did f of c. We just plugged in our c into f of x and used that equal to the mean value. Okay. And I'm going to make sure you know what that abbreviation is. All right, so now we just have an equation to solve. We can multiply both sides by c to the third. So 9 will equal to c to the third. We can divide both sides by 2. And then we're ready to do the third root of each side. So c will equal the third root of 9/2. That would be your exact value, and that would be approximately 1.65. We'll go to 2 decimal places on this, and that 1.65 is between 1 and 3, but it is not the midpoint. So you found the mean value of the function, which is 2, and you found the x where that mean value occurs, and that is approximately 1.65. Now, an alternative equation for finding the mean value is the definition that I have showing on your screen toward the bottom here. It's given in definition form. It's called the average value of the function on an interval. And if you'll study that equation is simply the mean value theorem solved for f of c. So It's just taken the theorem that was on the front and got the f of c by itself. So the mean value theorem solved for f of c. I really don't care whether you use this average value equation or whether you use the mean value theorem and just do the algebra to solve for f of c. Either one will get you where you need to be. So whoops, not for c, that's for f of c. So if you choose to memorize this average value equation, that's fine. But it is essentially the mean value theorem. So the next example asks you to find the average value of f of x equals 4 times x squared plus 1 over x squared. And so, and it also asks you to find all the x values. So in other words, all the c's in the interval where the function's equal to the average or the mean value. So I'll use the alternative form in this example to let you see how that is different. And then you can decide which one you want to use. All right, so using the average value form of the equation gets our variable by itself to begin with, and we'll have 1 over. So notice that I'm going from 1 to 3 again, so b minus a, 1 over 3 minus 1. And then I'll integrate also from a to b, so 1 to 3. And I am going to save myself just a little bit of time with my rewrite. I'm going to distribute the 4. So I'll have 4x squared plus 4. And I'm also going to write my x squared under each term to save a step as I do this rewrite. So we can begin the process of simplifying. This will be 1/2 the integral from 1 to 3. 4x squared over x squared. I'm going to finish the rewrite. That would be 4 plus, and then I want to write with a negative exponent 4x to the negative 2 power dx. So at this point, I would be ready to integrate. So I'll have f of c equals 1/2, and then my integral using the power rule is going to be 4x, and then plus 4x to the negative 1 over negative 1, evaluated from 1 to 3. And I can simplify a little bit. So I'll do that. F of c is going to equal 1/2. And just doing a little bit of simplifying, I'll have 4x, and then that'll be minus 4 over x, since that x to the negative 1 will move to the denominator, evaluated from 1 to 3. So now I'm ready to apply the fundamental theorem of calculus. So f of c will equal 1/2. And now I'll do my substitution. So I'll have 4 times 3 minus 4 over 3, and then minus, in parentheses, 4 times 1 minus 4 over 1. So there's the application of the fundamental theorem of calculus. And then we just need to evaluate. So f of c will equal 1/2, and then I just need to combine some numbers here. So I've got 12 minus 4/3 minus 4 plus 4. So the 4s are going to cancel, and I'll end up having 12 minus 4/3, and then that taken times 1/2. So I'm going to bring that over here. F of C is going to equal 1/2 times, and then 12, which would be 36/3 minus 4/3. I'll have 32/3. And so 1/2 of 32/3 is 16/3. My average value of the function is 16/3. And that was one of the questions. What is the average value of the function? So I'm going to circle that. I'm going to write that answer over here. The average value of the function is 16/3. Remember that average value is your f of c. So 16/3. All right, then we're also asked to find all the x's where that average value occurs. So to find c, we're going to use our original function using c in place of the x. So to find c, we'll take the original function. So 4 times c squared plus 1 over c squared. And notice I'm going back to the original. I think when you're getting ready to do this algebra, you really probably want to avoid the negative exponents. So we'll set that equal to the average value that we found, which was 16/3. So this is a good example of a problem to cross multiply. So we'll do that, and that'll give us 12. And we can go ahead and distribute 12c squared plus 12 equals 16c squared. So again, I took the 3 times the 4 and then distributed it. And then the c squared times the 16. Hopefully now you can see you want to subtract 12c squared from both sides. So 12 would equal 4c squared. Dividing by 4, we would get c squared equals 3. We'll do the square root of each side, and c will equal plus or minus the square root of 3. Now, the only value that is in the interval from 1 to 3, so we want to make sure we stay in that interval, c would have to be the square root of 3. So need to make sure that you use only the value or values that would be in the interval. So your average value is 16/3, and the c where it occurs in the interval is the square root of 3. So you'll have a few problems today that will focus on the mean value theorem and finding the average value of the function, and continue to ask for help as you need it. Well, we're going to work on some notes today for extra topics that Vincennes requires. And these are, first of all, bases other than e, where we take the derivative of those. And so we'll look not only at an exponential, but also at a logarithm, where the base is something other than e. So you have basically 2 new rules. The first one is doing the derivative where you have a base of a to a variable power. And so you'll notice that that derivative is the natural log of the base times the base to the power itself. And the alternative on that is if the exponent is something other than an x, then you need to multiply by the derivative of the exponent using the chain rule. For logarithms, where the base is something other than an e, then we will do 1 over the natural log of the base times 1 over x. And both of those then will end up being in the denominator. And then likewise, if the argument is something other than just an x, then we'll need to do the derivative of that argument. I've got your 3 properties of logarithms that you may have to use along the way, and a reminder that all other derivative rules still apply, like product and quotient and chain rule. So we're going to look at 2 examples to get started. The first one is where we have a base of 3 with a power of 2x. So doing the derivative with respect to x of 3 to the 2x, we'll first of all do the natural log of the base. So natural log of 3 times the exponential 3 to the 2x times the derivative of the exponent 2x, and so the derivative is 2. And then just to simplify that a little bit, just rearranging things, we could put the 2 in front of the natural log of 3 and then times 3 to the 2x. You might also see that written as 9 to the x power because you could go ahead and square the 3. All right, then your second problem is x times 6 to the negative 2x. And I tried to emphasize times because you're going to need to do the product rule. So we will start this off doing first times the derivative of the second. So like our last one, the derivative of 6 to the negative 2x is the natural log of 6 times the exponential itself, 6 to the negative 2x, times the derivative of the exponent negative 2. And then we'll do plus second, which is 6 to the negative 2x, times the derivative of the first. And the derivative of x is 1. So there's the calculus line. And then the simplification for that, we have 6 to the negative 2x as a common factor. We can take that out. And then rearranging just a little bit, we'd have negative 2x times the natural log of 6 plus 1. And those are your first 2 examples.